Go, champ. Nice. Thank you.
All right. Well, I'll give everybody a chance to either get seated or get out, whatever you're attempting to do at this moment. Hi, I'm Adrian Kaehler. I'm a technical person primarily. I am the founder and CEO of Giant.AI. I have been involved in startups for quite a while now, so I have some insight on that. When we get to Q&A, and towards the end, I'll talk a little bit about how the things I'm going to talk about through the bulk of the talk connect to startups and the entrepreneurial ecosystem. But the purpose of this talk, that's interesting. There was a start slide that we didn't start on. Well, we're going to start here. The purpose of this talk is to tell you all a little bit about what AI is and what it is not, and in particular what it is today and what it is not today. So people talk a lot about AI in a rather sort of speculative way and the future and what it can or can't or would or wouldn't be able to do. And it's very useful, I think, to have a little bit more concrete understanding of what is actually possible today and what is not. And to try to get beyond the mode of thinking in which AI sort of functions as this kind of magic genie in the bottle that will solve any problem, and to get a little bit more specific on what the actual reach of the technology is. So to start out, I want to just address for a moment just the use of the term AI. So in the 80s, AI was a very popular term, as also it was in the 60s and 50s, but it was completely not a popular term in the 70s or the 90s. And I thought I would address for a moment why it is that people say AI now and are not afraid to do so as they were 10 years ago. So what is AI? Well, to me, first of all, AI is really a description of a problem space. It's a class of problems. Now, not everybody in the field uses the terminology exactly the same way, but I typically use the term machine learning when I want to talk about an algorithm, something published in a paper, something you can write code about. That's machine learning. When I say AI, AI is an idea that's been around for decades. It refers rather to a class of problems, problems that humans are good at solving, problems that we quickly discovered back in the 50s and 60s that computers were not very well suited to solving, problems like recognizing a face, problems like understanding language, problems like simple robotic manipulation that is trivial for a 2-year-old human child, but somehow rather elusive for computers. So AI, to me, is about a problem space. Now, for a while, people were very optimistic back in the 50s and 60s that those problems were going to be solved with various technologies they had on hand. And then when they kind of overhyped it, you know, they got a lot of government money, and then it didn't pan out. And then everybody said, well, we won't use that term for a while, right? And then in the 80s or so, a lot of new algorithms came along, and people were very excited about those and what they thought they could do in the future. And so they overhyped it, and they raised a lot of money, and they got everyone very excited. And then it didn't really deliver, and by the 90s, everybody kind of went back into the closet and stopped using that term. So for some reason, a community of people that has been sort of beaten down a couple of times for getting a little too excited about this term has come back out of the closet and is willing to use this expression again. Why is that? And fundamentally, the reason for that is that a class of algorithms that allow us to do neural network-based computing in specific, a concept that's been around for a long time and never worked very well, really started working sometime in this decade. For many people in the field, the banner year is 2012, and a particular paper was published at a computer vision conference that used this neural network technology with very large neural networks, and it was able to achieve some spectacular results that everybody in that field was quite excited by. That domain of thinking continues in academia. This image up here is from a conference called NIPS, or actually recently renamed NeurIPS. But this is NIPS 2018. I'm in that picture somewhere in the back of my head. But there's 10,000 people at this academic conference. I remember a time when this conference had 500 people. Okay, so there's this enormous blossoming of interest in this kind of neural computing, if you want to call it that, but in particular what people in the field refer to as deep neural networks. So what I'm going to tell you about throughout this talk is two things. I'm going to talk a little bit about things that we can do with these algorithms. Of course, I can't give you a completely exhaustive list of everything that could be done, but I'll talk a little bit about some important things I think are important that can be done now. Okay, not speculating about the future, but now. okay? And I will talk a little bit about what it means to implement those algorithms at large scale, because it actually turns out that one of the most significant aspects of the development of AI is the scale at which it can be deployed, okay? So we'll talk a little bit about that. So this is an interesting slide. Professor Andrew Ng at Stanford, he's a pretty well-known guy in the AI field, so for those of you who are AI nerds, you may know his name. He kind of famously made this remark on Twitter. He said, pretty much anything that a normal person can do in less than a second, we can now automate with AI. That's a pretty good rule of thumb. He's a smart guy, and he was trying to give people a sense. It's kind of a lot of stuff you do with kind of your automatic brain, but not things that you really have to think through carefully. Not consciousness, but reflex in some sense. But, this statement is not one that's, without some contention. I went to grab this for my slide. I went to Twitter to clip it out. I was thinking, how will I explain that this is not something people universally agree on? But the very first comment on his comment that was even within screen-grabbing distance, this Pedro Domingos says, this is false and dangerous, humorous. Humans can do all sorts of things in less than a second. The AIs are nowhere close to matching. So then debate ensues, I don't know how many tens of thousands of tweets. But the point is that this rule of thumb that Andrew gave us, it's a good rule of thumb, but it is a rule of thumb. It's not an absolute statement. But it's a nice way to think about things. Somehow a lot of our automatic processes are things that we're beginning to understand how to capture algorithmically, but we're nowhere near getting close to the things that we tend to label as consciousness. So this talk will not be in any sense about artificial general intelligence or machine consciousness. Those things are, from my point of view, so far away that we wouldn't even know if we had them today. So let's look at some algorithms that exist. What can computers do now that they couldn't do 10 years ago that's of interest and derives from this AI field? One of them is that the process of converting speech to text, right, words, sound waves coming out of your mouth or whatever, into what is essentially a digital text representation as if you had typed it in a chat window. This is a problem people have been working on for decades, and it never really worked. It was always kind of flaky. And over the years, people came up with lots of very specialized techniques to do this, and a whole field developed in academia around it. But in fact, they never really got a system that worked. When this technology of deep neural networks came along, it was very easy to apply that technology to this problem and more or less immediately get a good solution. It was really quite an extraordinary achievement. The solutions that exist today, they have much hierarchy. This talk is not a technical talk. We won't get into all the details, but it's worth understanding just at a very gross level that, sound comes in and then it gets broken up into, phonemes, into little, audio bits and, recognized sounds. And then a lot of reasoning is required to string those sounds together into words. For those of you who are not per se linguists, you may not appreciate the fact that, when you write on paper, there are often spaces between words, but when talking, those spaces largely disappear. And it takes something of a trained ear to actually slice up the audio stream in a useful way. And then there's a lot of reasoning that's required because you don't actually hear me as well as you think you hear me, but when a word is somewhat garbled because of, reflections off the walls from the speakers or whatever, your brain kind of figures out what was the most likely word given the other things you did recognize. All of that has to be emulated by the machine in order to get decent, transcription to text. And this is one of the simpler achievements, but it's worth thinking about because it really changes the way in which we can interact with machines. And it turns out the way machines can interact with us. At a little higher level of sophistication, algorithms that allow some level of real understanding of what you're saying have also been developed using this kind of AI technology. And again, when I say AI, I primarily mean the machine learning technology of deep learning, okay? So the deep learning technology has allowed us to develop systems that, really have some sense of the semantic content of what you're saying. So in the old days, when, especially when people were analyzing just typed text as opposed to spoken text, right? The idea of understanding began with just written text or typed text. People did what was called, for example, sentiment analysis. If I typed, I hate Ford trucks or something in my Twitter feed, then the sentiment analysis would say, okay, hate, Ford, truck, okay, got it. He doesn't like Ford trucks. Like that was sort of what we could do. But in the last 10 years, the way in which we analyze that text is much more sophisticated. And a concept like, I would like to buy a Toyota Corolla for my girlfriend next year can be sort of completely understood. Okay, and not just, oh, that's a positive statement about Toyotas, but some kind of intent to actually make a transaction in a time frame and so on and so forth. Now, this, as I was saying, fundamentally, this technology is separate from speech to text, but of course they combine in a very important way to create technologies like this image here, I guess, is Amazon Alexa, but whether it's Siri or OK Google or whatever, being able to talk to the computer and have it actually kind of understand what you're saying is very important. And something that we do today with quite high reliability. On a slightly different front, another problem that's been around for decades that never quite worked is face recognition. Okay, so facial recognition is very important in the overall world of biometrics because it can be done at a distance, it can be done on a large group. A single image of this room could be analyzed and everyone in it, it could be identified, as opposed to, for example, fingerprints or something which require a personal interaction with the machine. The ability to recognize faces has come so far that this is now, this is in essentially every port of entry in the world, like every airport that has any kind of volume of passengers, the facial recognition is some part of the mix, for border security coming or going. In some countries, like just, last week I was traveling out of Shenzhen into Hong Kong, and the sum total of the border security in Hong Kong was I showed it my passport, it looked at my face, it decided I was the right person, and the door opened. Like there wasn't even a person there, right? That's the level of confidence that exists in this kind of facial recognition technology. Again, this is something that did not exist 10 years ago, and 10 years ago, before the advent of this deep neural network technology, people would have said, well, I don't really know when it's going to come, right? Before this new technological step opened a lot of new doors, people were saying, well, we'll get to it. It's working. It's getting better. I don't know when it'll work well enough. And then suddenly, it sort of worked well enough, right? And that's the recurring theme for a lot of these things that I'm going to talk about. Another thing is, it's not just your face. There's lots of other ways to identify you. And for example, cars have license plates, right? Why do they have license plates? Because basically, people can't see your face when you're in a car. So then if you can see the license plate, that's a means of identifying you, right? Now, again, these things exist at a large scale. It can be done visually. It can be done on an enormous space of cars, and license plate recognition is so robust and so inexpensive that it's gone from being used in high security border checkpoints or whatever to being part of the checkout process in a parking garage or used by a police red light camera. I mean, the deployment of license plate recognition technologies is utterly vast and, like I said, commercially very affordable. And you should maybe in your head automatically generalize this to, the tail numbers on an airplane or, any kind of street signs or this kind of, written text that's in some kind of standard format can be identified with extreme reliability. Okay, handwriting, things like that are slightly more difficult, but anytime you have a standard formatting for the text, this can be identified and read with extreme reliability. And that feeds these things kind of come together. Those are like ground level identification technologies that can be used, for example, to track someone or track something or figure out how things are moving around in the world, whether it's an individual or whether it's packaging or baggage or, parcels being moved around, whatever, drugs, I don't know, whatever it is you're trying to track, whether it's illicit or not. From orbit, we now have this kind of microsatellite technology. Now, this talk is not on data acquisition, it's on analysis. But in general, it's possible to look down from the sky in a kind of commercially viable way, image things that are going on at quite high resolution. And if you look at these images, it's possible to pick out every car in a parking lot. It's possible to pick out every plane on the tarmac. And it's possible to do that every frame, right? Which is to say, it's possible to track all those things through space. Now, interestingly, if you look really close at this image on the left, there's a few things that are marked as cars that are on top of that building, which are probably large air conditioning units. So none of these technologies are exactly 100%, yet. Maybe they won't be for some time, but they're robust enough to deploy at scale and use for business and government and other activities. Now, for the moment, I'm looking at these sort of in one by one, right? Just to kind of give you an idea what's possible. You'll see a lot of the things, the first couple of things I mentioned have more to do with audio. There's a lot now in imaging and video. That's also a place where these algorithms are extremely powerful. Those are also the fields in which they were sort of initially developed. So they're most robust and mature in those spaces. Now, there are other more subtle things. For example, when I talked about analysis of sentiment or understanding of language, some front end of that is converting speech to text or just collecting the text. But the understanding of that at a semantic level is a little more esoteric than just audio or video, right? It represents a little higher level of knowledge. Similarly, when you try to understand imagery or videos, there's a possibility for a kind of semantic understanding of video, sort of analogous, if you like, to the semantic understanding of audio. So, for example, this is a particular algorithm that analyzes kind of what's going on, right? It's a captioning system, which that's kind of a recurring topic in the world of AI, is captioning, sort of turning some kind of input into a string of human understandable text that describes the input. In this case, this is trained on a large database of movies, right? So they have all these movies, and they have their scripts, and they kind of teach the algorithm, and then they give it a movie that it doesn't know, or parts of a movie that it wasn't shown, and it has to figure out what's going on. And I don't know how many of you are familiar with Casablanca as a movie, but so you see up here, Rick sits down with Ilsa. Okay, that doesn't seem very challenging. Okay, great, we found Rick, we found Ilsa, we've decided they're sitting, not a big deal. But some of these captions are rather astounding, right? Back at the bar, Yvonne, an attractive young French woman, sits on a stool drinking brandy. Right? This is the kind of output which is possible from systems of this kind. Right? Now that's important because that represents a very high level of sort of semantically meaningful digestion of that video. Right? Well, in this case, when I say video, I mean video and audio. Right? But I think it's really important to understand that this is in reach. Right? Now, I'll talk in a moment about how reliable each of these algorithm types sort of is in the state of the art, but this is something that exists and can be done. So getting to that point about what they can do, there's a lot of plots here, and it's probably too much to digest, but let me kind of draw your attention, for example, to the big one in the upper right. This is plotting word error rate for an algorithm that's doing speech to text. Okay, so how often does it get it wrong, right? And it used to get it wrong, go back to 2012 when this first deep network technology came along, it would get it wrong about 16% of the time. That's a lot, that's like 1 out of 8 words. That's not so great, right? But over just the last couple of years, since that technology became available, the word error rate has dropped to about 4 or 5%. And that number is actually about the same as a human. So your personal word error rate isn't as good as you think. If you're a fast typist and you were sitting there writing down everything I said, and somebody came along later and actually compared a recording to what you wrote, you're going to be about 19 out of 20 words correct. So what you see is that not only has this technology started strong, got much stronger, it's also surpassed typical human performance, right? The one on the upper left is the image recognition benchmark. What's important about that is the same basic idea. It started good, it got better, and now it's better than people, okay? The one on the bottom right, I wasn't able to find a plot for this, but this is regarding this license plate recognition software. There's an open source software that you can just download and get for free that will correctly come up with all the digits of a license plate. 65% of the time, it'll come up with the top 10 guesses, and it'll be one of the top 10, and 42% of the time, it'll be the top one. Well, that's not great, but that's free, right? If you buy the commercial version that's trained on a lot more license plates, right, then it gets that license plate exactly right 99.2% of the time, and in the list of its 10 best guesses, the license plate appears up to the size of this data set 100% of the time. Okay, so a commercial grade license plate recognition system or any analog of that that's reading any other kind of standard text like, what's on your badge or whatever is going to be right basically all the time. So what I want you to take away from sort of this first half of the talk, even though I've used more than half of my time, is that there's a list of things that are quite significant that used to be sort of open problems that people didn't know how they would get solved that have now been, for all practical purposes, solved enough. Meaning the machines do it as well as a person might, and in many cases, better. Now, for the lower left plot, for those of you who have extremely good vision and a bit of a knowledge of the subject, would probably tell you, if you thought about it hard enough, that these video captioning systems are not quite there yet, but they're getting there, and they do very good work, but maybe not quite as robustly as some of these easier problems. So the next thing I want to steer your attention to is once you have a problem that is entirely digital, right? Once there's no person in the problem at all, right? Like my going through the checkpoint into Hong Kong, then the question arises, well, what's to stop you from scaling this out on a massive scale, right? Like, you might think, well, gee, how many people like voice-to-text, digital assistant, or whatever could we process in a day? But let's look at it in a different way. There are only some 10 billion people in the world. Now, why 10 billion? Isn't it less than that? Well, I was educated as a physicist. So we mostly just count the zeros. It's like an order of magnitude calculation. So it's like 10-ish, okay? You might ask, well, what about everybody, right? Like, could you do everybody? How much compute does it take to take everything everyone says every day and convert it to text, for example? So I mentioned my background in physics, so I'm a big fan of chalkboards, but unfortunately the closest I'm going to get chalkboard is this slate-covered square up here, but let's compute. So it turns out an average person speaks about 16,000 words a day. At 150 words a minute, which is also average, 60 seconds per minute, about 6,400 seconds per day you actually output in speech. The most processing efficient speech-to-text algorithm that I'm aware of, in about 47 million operations, it can convert 1 second of audio into text. Now, 47 million operations, where does that come from? Well, it's basically telling you how many neurons there are in that neural network, right? It's like, for every neuron, you have to do some little bit of bookkeeping and then, take that answer and give it to the next neuron and so on. And so by knowing the size of this neural network, you can figure out how many operations are required. Now, that's 300 giga operations. And the giga is probably something you all have in your head, but we're going to quickly make our way to ones that everybody forgets. So I put this convenient chart on the bottom left. So, giga is 10 to the 9th. But if you want to do this for 1 billion people, then that requires 300 exa operations, right? How much the exa operation? Well, again, check the chart down there. It's a lot. Okay, but the key point is, one top-of-the-line graphics processing unit that supports the necessary infrastructure to do neural network computing as well. NVIDIA's products have largely gotten to a point where they pretty much all do this, right? The top-of-the-line GPU that NVIDIA sells, called a Titan V, will compute 110,000 giga operations per GPU per second. Okay, 110 teraflops for those of you who think in those terms. Well, that's a lot, right? Because that means there's a lot of seconds in a day. This processor will compute 9.6 exaops per GPU per day. Okay? So remember, checking the chart, there's a lot of zeros in an exa. That's 10 to the 18th power, right? If you divide, what do you get? Only 32 GPUs, right? That's for 1 billion people. They're only $3,000 a piece. That's 100 grand. That's a Tesla Model X, right? Like, there are lots of people in this room who could afford that many GPUs, right? It's like, that's a high-end car, right? It's not a huge amount of money. Now, I'm being a little glib with the costs, right? That's just for the GPUs. In real life, you got to put them in some server rack, and there's got to be a co-location center and whatever. But, tax and tip, it'll be, 5x that or something. But the key point is, this is a very terrestrial number. This is for 1 billion people, right? That's 1,000 Estonias, right? What about the hard problems? This activity recognition I talk about is kind of the hardest problem that we can actually do of the kind that I mentioned. So with this kind of thing, you have to analyze every single frame of video, right? That's a lot, right? So there's 30 frames a second, let's say, in a typical video stream. So that means 2.5 million frames per day have to be analyzed in order to, figure out what somebody did all day, right? I mean, I included their sleeping. That part's probably easier, but you never know. They could wake up in the middle of the night. Who knows what might happen? So that's the total number of frames. This particular algorithm, you have to kind of dig into it to figure out where all the time gets spent. It's quite complex, but the bottom line is most of the time is spent in an image recognition pipeline that's pretty sophisticated, and that thing takes about 100 million operations per frame. So that vision pipeline takes twice as much compute for a single frame as takes for an entire second of audio, right? So, okay, you just go through the calculations then. So per person, you need 258 tera operations per day. Check the chart if you forget. So for 1 billion people, 258 zeta ops, right? You're all used to giga and tera is the new thing, but here's exa and zeta right in front of your face. Okay, 260 zeta ops. Now take that same Titan 5 GPU at 9.6 exa ops per day. What do you get? Okay, 26,875 GPUs. Okay, that's a lot. I mean, that's a lot of GPUs. But what is that in dollars, right? Well, they're only $3,000 a piece, so that's $80 million. That's the price of Sergey Brin's yacht. Okay. Now, not many people in this room probably have an $80 million yacht, but what does that mean to us in practice? It means to analyze, assuming you had such a video stream, to analyze what goes on for 1 billion people, right, requires a quantity of resources sort of equivalent to like the kind of yacht that a bad guy would own in James Bond, right? That's for a wealthy person, that's achievable individually, though such people are rare. For a corporation, that's a very tractable amount of money. And for a state actor, that's a trivial amount of money, right? So, here in the EU, the fighter jet du jour, right, is typically $400 million a unit or something like that for an F-35, right? This is like old F-22 technology. Just single fighter jet buys you enough of these resources to analyze the activities of a person for an entire day. And if you want to do all the other things that I talked about together, what you're going to find is it doesn't cost much more than this, because this one is the most expensive of them all. So I'm running out of time. Actually, I'm over time, so I'm going to wrap it up pretty quickly. But I want to point you to some simple conclusions, right? Not that you're not already there in your heads, but just to spell it out. The downside, massively intrusive surveillance on a planetary scale, right? It is possible to track every single person, everywhere they come from, everywhere they go, everything they say, analyze it all, right? And that's a big change, because many of us in this room